All right, given a graph G and a weight function on the edges of G, so for every edge we associate a real number, and then given a subgraph of G, we're going to define the weight to the subgraph to be the sum of the weights of the edges of the subgraph. So for example, if I take my graph G to be the 4 cycle, and I label the weights of the edges as 1, 2, 3, and 4, and I take my subgraph to just be this bottom corner, path of length 3, then the weight of the subgraph is 1 plus 4, it's 5. Then we define a minimum weight spanning tree to be a spanning tree with the property that it has the minimum weight. So given any other spanning tree T prime, our spanning tree T is smaller weight. Note we use less than or equal to, so we're not guaranteeing that there's a unique spanning tree of minimum weight, just at least one. Given that the collection of spanning trees of a finite graph is a finite set, we do know that a minimum weight spanning tree must exist. So here we discussed our first algorithm for how to find a minimum weight spanning tree. It's called Kruskal's algorithm. The basic idea is that at each step you create the minimum weight forest on k edges, and you keep doing it till the algorithm terminates. So that explains the logic. We start with every edge as a possible candidate, and our forest starts as the empty set. And so as long as there's a candidate edge left, we take the minimum weight edge in that set X. Then we remove that edge from consideration, and then we just check whether or not adding it to our subgraph creates a cycle. So in the initial step, that's guaranteed. As long as E is not a loop, we should be able to add it. So the point is, if you can find the minimum weight edge that you haven't considered yet and add it to your graph and get a forest, we're going to add it. And we're going to keep doing it till we run out of candidates. And then the claim is that by the time the algorithm terminates, the resulting forest we have will actually be a spanning tree of minimum weight. So let's do an example with this graph on 5 vertices and 7 edges. So since there are 7 edges, there's going to be 7 steps. The first step is we take an edge of minimum weight. There's 2 possible options. We decide to take the edge AB. And since adding AB to our subgraph, which is currently the empty set, does not create a cycle, we add it. So our first step, we have a forest with 5 vertices and 1 edge. Next, we take the minimum weight edge and what's remaining, and that's going to be the edge DE. We see that if we add DE to our graph, we don't create a cycle, so then we add it. Now we take the minimum weight edge of what's left. We see 2 is the smallest number remaining, so we take the edge BC. We see that if we add it, we do not create a cycle, so we're going to add it. So now we have, in the remaining edges, we have 2 of weight 3. So we choose the edge CD arbitrarily. We see that if we add the edge CD to the graph, we're going to get a path that's not a cycle, so we add it. Now we consider the possibility of adding the other edge from A to D. We see now that adding it would create a cycle, so we don't add this edge, but we mark it to point out that it's been considered before. And now all that's left are these 2 edges of weight 4 and 5. In both cases, adding them would create a cycle, so we don't add them. And so once the algorithm terminates, we see that we have this tree. It is worth noting, if you go back through the algorithm, there were points where we had multiple options of what to pick. So I will point out that if you pick the edge AD first, you just replace the edge CD with the edge AD, and you'd have another path, in this case, of the exact same weight. And it's also worth pointing out the weight of this spanning tree is 7. So again, the idea is that we keep taking the minimum weight edge available and keep adding it to our forest as long as we don't create a cycle. And we keep going until we run out of edges. It turns out there's another algorithm for finding minimum weight spanning trees called Prim's algorithm. Here, the idea is that instead of creating a forest and adding edges one at a time, we're going to create a spanning tree for a subgraph one edge at a time. So here you have to start with a vertex for your spanning tree. So we start with one vertex, and we're going to slowly add vertices to this set. And we're going to start with no edges. So at each step, we're going to add a vertex and an edge. So as long as we haven't reached every vertex in the graph, we're going to define the set S to be those edges that have exactly one endpoint in our subgraph W. So the idea is that as we go, we have a W, we're looking at all the edges that have one endpoint. The point is we're going to choose to add one of these specifically to create a larger W. And so that's the strategy. We let S be the set of edges that have exactly one endpoint in our subgraph W. Then we're going to choose an edge in S of smallest weight. And then we're going to add both endpoints of that edge to W. Note that that means you're only really adding one new endpoint. And then we're going to add that edge to our set of edges, X. We can see at each step the reason why the resulting graph is going to be acyclic is because at each point we've added a new vertex to our subgraph. And the only way to get a cycle you'll see is if it turned out both endpoints were already in our subgraph. So now we're going to try running Prim's algorithm with our same graph again. I have to pick a vertex to start with. I'm going to pick the vertex C. So the point is I'm going to look at all the edges incident to C because those are the edges that have one endpoint in our set of vertices. And I'm going to pick the one with minimum weight. And it turns out to be this edge right here, BC. So I'm going to add it, which means I've added the vertices B and C to my set. So now at the next step, these are my two vertices in my subgraph. And these are the edges that have one endpoint incident to it. And so I see the edge labeled 1 is the minimum weight. So I add the edge AB and the vertex A. So now my set consists of the vertices ABC and the edges AB and BC. And now if I look at my edges that have one endpoint in S, it's these four edges right here, everything but this one. And I see there are options of minimum weight edges. I'm going to choose AD this time. And so now I've added the edge AD to my graph, and now my red vertices consist of A, B, C, D. I see that edge BD and edge CD both have both endpoints in my subgraph, so these are no longer in the set S. Now my set S only consists of these two edges. And so I see there's an edge labeled 1, I add it, and this is my spanning tree. So one thing you will notice is that in both cases, both algorithms, we are guaranteed to terminate with the spanning tree. For Kruskal's algorithm, it's because we choose not to add any cycles, and here it's because at each step we have a spanning tree of a connected subgraph. However, it's not entirely obvious that in both algorithms we're always making these choices of taking the smallest edge. It's not guaranteed that we know we're going to get the minimum spanning tree over all, so that requires a proof. For this class, we're going to give the proof that Kruskal's algorithm always produces a minimum spanning tree. There is one gap in this proof. We're going to assume that the algorithm is guaranteed to terminate in a spanning tree. That just means that you have to guarantee the final forest is in fact connected. And that's not too hard to prove. You do proof by contradiction. Suppose it's not connected, then there's two components, and then there has to be an edge between those components. And then you just point out that adding that edge would not create a cycle, and therefore the algorithm had to have added one of those edges, a contradiction. Just similar to what we're going to do here is a contradiction argument. So we're going to let T be the spanning tree produced by our algorithm. I'm going to label the edges 1 to en minus 1 to be the order in which the edges were added by the algorithm. Now we're going to let T prime be another spanning tree. We want to prove that T prime's weight is at least T's weight. And this proof is going to be on induction on the number of edges in T prime that are not in T. Note that we're skipping the base case, so we're assuming that there are edges in T prime that aren't in T. Since both sets have the same number of edges, that also means that there has to be edges in T that aren't in T prime. And so we're going to let I be the smallest integer where e sub I was not in t prime. Suppose, for example, that this was our spanning tree from earlier, and this is a different spanning tree for the same graph. We see they disagree in certain edges, and so since there's an edge in the red graph that's not in the blue graph, there has to be an edge in the blue graph that's not in the red graph. In this case, it's E3. So the idea is to add the edge E3 or EI to our subgraph, as so. And since we know from our properties of trees that a tree is maximally acyclic, we know adding an additional edge must create a cycle. In particular, it has to be a cycle with that edge. Then since in the blue sub-spanning tree, T can't contain our cycle, that tells us that there has to be an edge on the cycle that's not on our tree. And since the cycle consists of edges of T prime, with the exception of this EI, that means this edge E prime has to be in T prime but not T. So the whole point is that we found some special edge E prime that's on the same cycle as EI. And the whole reason why we're going to do this is because we're going to replace E prime with EI and get a tree of smaller weight than T prime. So that's the next step. We let T double prime be what happens when we take our spanning tree T prime and swap the two edges. And because we've swapped two edges along a cycle, it turns out T double prime is a tree. That takes some effort to prove, but it can be proven using our tree properties. And we want to prove that it's of smaller weight. Then, because T double prime has one more edge in common with T than T prime did, we can use induction to claim that the weight of our minimum spanning tree is less than or equal to the weight of T double prime. And so by these two inequalities, we can conclude that our minimum weight spanning tree actually has minimum weight. And so to give a sketch of the first claim that T double prime is a tree, we show that T double prime has to be maximally acyclic. So the point is, consider any cycle in T prime that existed. If EI is not on this cycle, then it's a cycle in T double prime already, which is a contradiction. So then the point is EI has to be on the cycle. So it has to look like this. And then you see the point. The point is that then if I take the cycle we had earlier with the edge E prime and I remove EI, I get a new cycle in T prime. Again, a contradiction. Therefore, this graph has to be acyclic. Similarly, if you add any edge to T double prime, you add an edge to T double prime, then just go ahead and add that same edge. If that edge were EI, we're done because you already have this cycle. E prime, we're done. If not, then you could add it to T prime and get a cycle C prime. And again, if that cycle does not involve either of these two edges, then it's a cycle in T double prime as well. If it has that edge, then you just do the same trick where you add the other half the cycle on, and now you'll create a cycle in T double prime. So this tells you that T double prime is maximally acyclic and therefore a tree. So for the next step, we need to show that the weight of our T double prime is at most the weight of T prime. Since these are defined as the sums of the weights of the edges, we see that the difference between these two comes down to the weight of E prime minus the weight of EI. So all we really need to show is that the weight of E prime is greater than or equal to the weight of EI. All right, so what we do is we consider the point at which the algorithm added EI to F. If E prime was an X at that point, then by choice of EI, the weight of EI must be less than or equal to the weight of E prime, which is exactly what we want to show. So then there's one other case, that's if E prime was not in X at that point. Well, then that had to have been removed from X by the algorithm, which meant there was some point where the algorithm considered it, which means there's some j less than I where all we've added to our set F so far is E1 through EJ, when the property is that the weight of E prime had to be the smallest weight of all the things in X at that point. But since E prime is not in our set T, it must be the case that E prime is not EJ plus 1, which means our algorithm did not add it to F, and the only time our algorithm considers an edge of minimum weight and does not add it is when adding it creates a cycle. So then we must be in the case that F union E prime has a cycle. But remember, we defined E sub I to be the smallest edge in T that's not in T prime. So since j is less than I, the edges E1 through EJ are in T prime. And so the set F union E prime is in T prime, which means T prime has a cycle, which is a contradiction. Therefore, this second case can't happen. It must be the case that the edge E prime is available to study when we reach the point in the algorithm where we add EI. And thus, we do have this inequality on weights.